When we evaluate an algorithm, we aren't counting individual milliseconds. We are measuring structural scalability. As an algorithm processes inputs approaching infinity, flat constant values drop away, leaving only the mathematical engine driving the growth. To understand how software behaves at scale, we have to rank these underlying functions. On the graph tracking growth toward infinity, these three curves, logarithmic, polynomial, and exponential, do not just diverge, they move into entirely different scales of magnitude. In this hierarchy, any exponential function will eventually overtake any polynomial, and any polynomial will overtake any logarithm. Inside these categories, specific rules apply. Swapping a logarithm's base from 2 to 10 changes only a constant multiplier, keeping it in the same class. However, changing a polynomial's degree, moving from n squared to n cubed, shifts it into a different growth tier. This analysis maps functions in the lower tiers of growth, starting at the floor of pure constants and stopping at the ceiling of n cubed. Establishing this baseline order is the required first step for evaluating any software system, as it provides the coordinates needed to locate an algorithm's cost on the growth map. We anchor the bottom of the hierarchy with the constant value of 1. This represents an algorithm with zero growth, an operation that takes the same amount of computing time whether the input is 10 items or 10 billion. Consider the expression n to the 1 over log n. With the variable n sitting in the base, the function appears to scale as n increases. To find the true growth rate, we can apply the identity where n is equivalent to 2 to the log n. Substituting this into our expression gives us 2 to the log n raised to the power of 1 over log n. When we multiply these exponents, log n and 1 over log n cancel out, leaving only the constant 2. The CAS asymptotic notation ignores constant multipliers. The value 2 belongs to the same equivalence class as the constant 1. Algebraic substitution often reveals that visually complex functions actually belong to much simpler growth classes. Slightly above pure constants is the iterated logarithm, written as Lg star n. The star notation indicates that this function counts the number of times we must apply the logarithm to a value before it reaches 1. To see how slowly this value increases, consider a number like 2 to the 65,536, a value exceeding the estimated number of atoms in the observable universe. The iterated logarithm measures how many steps are required to reduce this massive scale down to a constant. The first log application reduces our universe-size number to 65,536. The second brings it to 16, the third to 4, the fourth to 2, and the fifth application reaches 1. For any input size that can physically exist, the iterated logarithm will not exceed 5. If we nest this function, as in the iterated logarithm of the LGN, we are simply adding one more log application to the start of the process. This makes Lg star Lgn equivalent to Lg star n minus 1, a negligible difference in asymptotic terms. Even when used as an exponent, such as 2 to the Lg star n, the function remains beneath the growth rate of any standard logarithm. The iterated logarithm technically grows toward infinity, but it does so at a rate that allows it to be treated as a constant in nearly any physical application. Above the constants, we find the polylogarithmic tier, functions like ln ln n, square root of lgn, and lg squared n. On a graph, these curves consistently bow toward the horizontal axis. Swapping the base of these logs, from base 2 to the natural log, alters the vertical scale, but does not change their underlying growth class. The function square root of 2 to the log base 2 of n presents a different profile, as the variable n appears in the exponent. By rewriting the square root of 2 as 2 to the 1/2, the exponent becomes 1/2 log base 2 of n. Using logarithm rules, we move the 1/2 coefficient inside the log function, where it becomes an exponent of n. The base and log cancel, leaving us with square root of n. On the graph, the curve now shows clear polynomial curvature. This leads to the linear class, n. Similarly, the expression 2 to the log base 2 of n simplifies directly to this linear path. We have now moved from logarithmic growth into polynomial space. From this point forward, even the weakest root, the square root of n, will eventually dwarf the most powerful polylogarithm. Above linear time is the superlinear class, theta of n log n. The growth rate of log of n factorial tracks along this same path. Next, we look at the function 4 to the log n. Because the variable n is in the exponent, this function is often grouped with exponentials. We can test this by using the identity a to the log base bc is equal to c to the log base ba, which allows for the swapping of the base and the log's argument. When we swap the 4 and the n, the expression becomes n to the log n. Since log n is 2, the function is actually the quadratic n squared. We can apply the same identity to more complex structures, such as log n to the log n. Swapping the base log n with the argument n gives us n to the log n. Because log n grows very slowly, the exponent of n increases at a minimal rate, placing this function between linear and quadratic growth. This base swapping identity is the primary tool for determining if an exponential expression is actually a polynomial in disguise. This map now spans from the horizontal line of constants through the logs and the linear path of n up to the steepening ramp of n squared. When we add n cubed, it covers more vertical distance than all previous functions combined. The curves for n squared and n flatten relative to this new scale. Visually, the n cubed curve appears to move toward a vertical line. However, in the context of higher growth rates, n cubed is still categorized as a polynomial. Beyond the reach of these polynomials lies a different scale of growth. This space contains functions like 2 to the n and the factorial and factorial. These functions diverge from polynomials as sharply as polynomials diverge from constants. To measure them, we must apply the tools of Part 2. This map spans from the horizontal line of constants through the logs and linear path of n up to the steepening ramp of n squared. Adding n cubed covers more vertical distance than all previous functions combined, forcing the n squared and n curves to visually flatten. Visually, the n cubed curve appears to move toward a vertical line. However, in the context of higher growth rates, n cubed is still categorized as a polynomial. Beyond the reach of these polynomials lies a different scale of growth. This space contains functions like 2 to the n and the factorial and factorial. These functions diverge from polynomials as sharply as polynomials diverge from constants. To measure them, we must apply the tools of Part 2.